All right, thank you very much. Good evening, everyone. As has been said, I'm Dr. James Lees, and I'm an associate lecturer at the University of York. I've had what you might describe as a very varied career in physics, and it sounds like things are going to keep varied as I'm currently looking into doing quantum communications as my next role. So I like physics. I like all sorts of physics, but my first love is astronomy. That's how I got into physics in the first place, and I still stick around doing lots of astronomy things these days. Right, so today I'm going to talk to you about all these worlds, the wonderful and weird worlds of exoplanets that exist within our universe. Now, before we start talking about exoplanets, and you may not know what that word means, we first need to define actually what is a planet. It's a seemingly very simple question, he says, seeing if his clicker is going to work. If not, that's not a problem. Hang on. It's fine, I can do it this way. Right, so what actually is a planet? This is something that we need to be able to define before we can talk about an exoplanet. So the first things first, it has to orbit the sun. That's a pretty simple idea that if we want to have something that is a planet, it must be orbiting the sun. And this is the important part, that it is the sun, not a star, because basically that's the exoplanet, but we'll get back to that in a moment. But when we're talking about orbiting the sun, we're talking about orbiting the sun exclusively. So this means something like the moon, which orbits around the Earth, therefore cannot be a planet. And why that's an important distinction will come up again later. The next thing, lots of stuff orbits the sun. A huge amount of stuff does that. So people then decided, okay, what is our next definition to this going to be? And they came up with the idea that it must have sufficient mass to be round or round thereabouts. Because, of course, the Earth is not a perfect sphere. It is an oblate spheroid, which means it's slightly bulgy in one direction. So in order to mean that every little rock and scrap of dust isn't decided to be a planet, it was decided that, okay, it's got to be big enough such that it's got enough gravitational pull that it's going to sort of sand off its own edges. Third thing, must not be a satellite of another object. Now, this is a slightly interesting one. I brought up the idea that the moon doesn't orbit the sun, but rather orbits the Earth. But actually, when you sort of lay these things out, it looks more like it is actually orbiting the sun. It's all a matter of references and what it looks like from different positions. So basically, people realized that that first rule didn't quite work. We wanted a distinction between a moon and a planet. So, okay, satellites of another object. It must orbit the sun, but it must primarily orbit the sun and not something else like our moon does. This all makes sense so far. We're pretty happy with this. You know, all those rocks and asteroids and comets that exist, we don't want those to be planets. And that's an important part here. We don't want them to be planets because planet is a very arbitrary distinction. What separates a planet from a pretty large rock is something that we as humans have had to decide. Now, these sort of rules here have been around for a long time. People have been happy with these. But it was in 2006 that we came across a problem. You see, many moons ago, back in the sort of Victorian era, there were a few other planets that we don't typically talk about today, Junos and Ceres. Now, these were orbiting the sun. They were near enough round, and they also weren't satellites of other objects. But it was later discovered that they were part of the asteroid belt. And effectively, if we counted them, we needed to count a lot more planets. And planet has this sort of special connotation. We don't want to, open up this wide, broad idea of what a planet can be. We want them to remain relatively small and special. So this is where the fourth and final ruling comes from. It must have removed the debris and small objects from the area around its orbit. And this is the one that caught out Pluto in 2006. The idea that if it's just one big rock in a whole load of rocks, well, that can't make it a planet. And we can see the sort of difference if we jump to something like this. So this is, obviously, it's a not very realistic representation of our solar system, but it gets the point across. So we've got the main planets that we have here. But then if we look into the asteroid belt here, you can see there's some pretty big rocks. And some of these rocks are relatively comparable in size to Mars. They're probably a bit bigger here than they are in real life, but, you know, they're still pretty big rocks. The problem then was, well, when we looked out into deeper space, we found Pluto that we were looking at, and Pluto is effectively another large rock. And for a while, that was fine until it was pointed out that, well, there's a lot of other rocks out there as well. And if we count Pluto, we've got to start counting all of these other ones. And we found a good handful of these, what we now call dwarf planets, which are the planets that they fit most of the definition, but don't manage to get to that point where they've cleared all the rest up. They hoover it up as they go around in an orbit, much as the same way the fact we get meteor showers as we pass through areas of stellar dust. Same idea here, except much, much bigger obstacles being hoovered up by a larger planet. Now, that is what gives us our planet. And as I said, it's rule one that we violate for an exoplanet. An exoplanet is a planet around an alien sun, a different star to our own. And there are, as of the most recent figures I could find were from July, over 6,000 of these exoplanets confirmed. We know that there are nearly 7,000 exoplanets out there, and we have another 9,500-ish of candidate exoplanets. Planets out there that we think might well be exoplanets. Now, this is either a very big number or a very small number, depending on how you look at the situation. Because, of course, that's a lot of planets, thousands and thousands, that's a lot out there. And, this is probably just a few of the ones we found. And that's the kicker, actually finding them. Because if we think about it, there are tens of thousands of stars, hundreds of thousands of stars if you're using telescopes. There is even more than that well beyond our galactic plane. So actually, compared to the number of stars that we're looking at, we're not seeing a huge amount of those planets. And again, that key is in the word seeing. It is not necessarily that these exoplanets don't exist, but rather that it is very, very hard for us to spot exoplanets. We can't just take a picture of them. Even with things like the new James Webb Space Telescope, it's not like you could snap a nice picture, Almost all of the pictures I'm going to show you today are artists rendering for the exact reason that you can't just take a nice picture. I mean, it took us until relatively recently before we could even get a decent picture of the surface of Pluto. So if we're struggling to do it with the exoplanet type things within our, some of the planets within our own solar system, you can imagine that it is very difficult, nay, impossible to be able to get the pictures of them from other solar systems. So here is the question then. If we can't just take a picture, how do we actually spot these exoplanets in the first place? How is it that we can take a look at them and know that we have these 7,000-ish planets and 9,500 more potential planets? Well, there's a few different methods, and I want to run through them with you now. The first and the main method is the transit method, and this relies on a simple formula of if you put something in front of a light source, it's going to look a bit dimmer to anyone it's between. And this is the kind of thing that we do. So this nice little GIF here, what we have is we have a star, and as we pass a planet in front of it, what you're going to notice is the amount of light that we see drops. Now, that's quite a dramatic drop on the graph there. It's going to be much, much smaller in real life, but it's like sitting in your chair and someone walks in front of the television in front of you, right? As they pass in front of you, the amount of light from the television reaching you is going to be a lot less. And if we have sensitive enough telescopes, we can measure that drop. Not only can we measure the drop itself, we can measure, how much of a drop there is. And in measuring how much of a drop there is, we can say, well, based on our calculations, that means that the planet is probably this big. Not only that, we can also look for that drop happening again. And this is where we make generally the main distinction between having an exoplanet confirmed and an exoplanet candidate. Because the big problem that we have here is, well, lots of stuff passes between us and any given distant star. And we might not be looking for something the size of a planet. It could be something within our own solar system. It could just be an asteroid or a comet or even just a cloud of dust that passes between us and that star. There's a lot of space in between us, so it could be just about anything. And that is why one transit is not enough. We need at least two transits that look exactly the same to make our exoplanet go from candidate to confirmed. So when we see one of these dips, and we can have a telescope focusing on hundreds, if not thousands, of different stars all at the same time, when we see a dip, that goes into a catalogue. And it's only when that same dip gets seen again that we know that it is a real planet. And of course, we can get information from that second dip, not least how long is the difference between the two of them. Did it take a long time? Did it take a short time? And that can tell us what the orbital period of our our transiting planet is. Now, this is not a perfect method for quite an obvious reason, in that the planet has to pass between you and the star. And that is only going to happen on a relatively small orbital plane. If you think about all the possible different orientations that it could be in, it needs to be in quite a precise area for it to pass directly between you and this star. So it's a really good method, but it's not perfect. So we need some other tools in our toolkit. One of these is the radial velocity method, and this is where we measure the radial velocity of a star. And the way that we do this is relatively simple. If we have a big star and a big planet, and they do both need to be big, what's going to happen is, technically, the planet does not orbit the star. They both orbit the center of mass between them. Now, typically, that basically means they're just orbiting the star because the star is absolutely huge. But if your planet is big enough, it can actually cause a little bit of a wobble in the rotation of the star. Now, the picture that we're looking at here is super, super, super exaggerated. It's not going to be nearly as large as this. In fact, it's only really going to be a tiny wobble, but there's going to be a change there. And what's important about that is we can measure that. There's something called pitch shift. You might have heard it before with the Doppler effect, where if a ambulance or something is coming towards you, or even just a car zooming past, it gets a higher pitch as it moves towards you, and then as it moves away, it gets lower pitch. And this is happening because the waves that are the sound waves from the ambulance, or in the case of a star, the light waves that are coming from it, get more compressed as they're being moved towards you, because each successive peak of the wave, the object is physically a little bit closer to you, and alternatively, once it goes past, the start of each wave is again slightly further away from the last one because the physical object has moved. So we can measure this. Now, for stars, it's not looking at the pitch of the sound, but it's looking at the pitch of the light, or the frequency of the light, which, as it's moving towards you, shifts into the bluer end of the spectrum. And as it moves away, it shifts down to the redder end of the spectrum. So that's basically what we can do. If we watch a star, and if we can see this nice, clear, periodic change in its color, getting ever so slightly bluer and ever so slightly redder, and backwards and forwards on a predictable pattern, that tells us that there is another very large object that are orbiting each other a little bit like this. So that is another way that we can look for planets. Another method is microlensing, and this is using gravitational lensing, which is one of Einstein's theories, which we eventually discovered, but the idea that light bends around very large objects. And if your very large object happens to be a planet, what you can get is a smearing out of the light to the star. The star should be a pretty much perfect sphere, or from our point of view, a pretty much perfect circle. But if there's a very large planet there, it can cause some of that light to go awry. Now, the picture that we're looking at here is not, in fact, a star and a planet. It's actually a galaxy that is being smeared around the outside of a particularly large black hole. But what we're looking at here is that the light is coming past this massive object, and it's being bent around it. Now, this is an extreme version, but we can basically do the same thing again with our planets. If you've got a nice big planet, as it passes by the star, what you're going to see is the light changes from the star. We're looking for a slight variation in the pictures, and that will be able to tell us how big is it, how far away is it, all that sort of good stuff. Now, I said we can't take pictures of exoplanets, and that's not quite true. They're just not necessarily the kind of pictures you would want to or expect to see. See, we can actually take direct images like this here. So this is a particularly large star with quite a large planet around it, HD 106906b. Astronomers not being the best at naming things, especially when there are literally thousands of them to name. But what we can do here is we can use some special kind of interferometry techniques to be able to take these very, very far away pictures. But what you will note here is that we have this star in the center here, but in order to detect the planet as a separate entity, it's a really, really far way away, 650 astronomical units, which you can compare there quite nicely to Neptune's orbit being just 30 astronomical units. So in order to be able to distinguish these, in order to be able to take the direct images like this, it's got to be a big planet again, and it's got to be really, really far away. Otherwise, it essentially just gets drowned out by the light of the sun. Now, even cooler than that, what we actually be able to do is if we put some of these together, we can actually make a movie of the orbiting of some of these planets. So what we have in the center here would be the star. It's blacked out in order to, remove some of the light so that we can actually see the other stuff. That's why you can see this sort of coronal effect that's coming around it. And we can actually see a few different planets that are orbiting around the star here. Now, you'll notice this is a series of images that are taking place over just under a 10-year period, and they're not getting very far at all. They're very, very far away from their star, so we can't see a full rotation. They're quite far out in this particular instance. Okay, that is the main methods. There are other different methods that people try, but those are the main ones. And the question then is, okay, how good is each of the different techniques? Well, we can split them up like this. And again, this is using the July data. The vast majority of the exoplanets that we find, they come from the transit method. It's relatively simple and it's quite easy as well. All you've got to do is point a sensitive telescope at a whole bunch of stars at the same time and look for the light dips across them. You can get computers that are able to deal with the hundreds or thousands of stars all at the same time. So that is the main method at the moment for picking out all of these new exoplanets. Radial velocity, very similar again. All you're doing is you're looking for that change in light. You can look at a whole bunch of different stars at the same time. Direct imaging, a little bit more difficult. Micro lensing, these are a lot less, partially because you need to give quite a lot of time and effort to finding the right place. And you also need to have particularly large planets because in order to be able to cause that micro lensing, in order to be able to be big enough and far enough away while still orbiting properly, it's got to be big, and therefore there's going to be fewer of them to find. And as I say, there's a bunch of other different assorted methods which we also use to find them. Okay, that's cool. There's lots of planets out there. But what are they like? What do these planets actually look like? What's going on with them? Well, we can break them down into a few different types, and they are quite simply rocky, gaseous, and icy planets. And for very obvious reasons here, I've used ones from our own solar system. Our solar system is probably not very unique. That's probably a good idea in sort of universal terms, that there probably isn't anything special about our place. So it makes sense that we have all of these types. So rocky planets makes a lot of sense. It's a lot of condensed rock, make a nice solid surface, very much like the Earth that we live on. It can be made out of all sorts of different things, but it's a solid lump that exists, and typically these are relatively small. The main type of planet are the big gaseous giants. So these, like Jupiter, are generally pretty big. They are pretty hot, and they are mostly made of gas. Now, that's not to say that you would be able to sink all the way through them, but they're mostly made. Sorry, this is Saturn. I don't know why I said Jupiter earlier. But what we're looking at here is we're looking at big balls of gas, mostly hydrogen, a little bit of helium. In fact, many of these, especially the big ones, are often called failed stars. And that's because if these were much bigger, they would turn into stars. They are the protostars. And in fact, if you were to take one of these and you siphoned off more hydrogen onto it, they can eventually catch light, start undergoing nuclear fusion, and turning themselves into stars. Ice giants are basically the same thing. It's just they are far enough away from their own star that it's cold enough that they turn mostly to ice. Now, the question might be, well, if they're far enough away from the star, the background temperature of space is somewhere in the region of 2.3 Kelvin, which is like minus 270 degrees. It's not very far above absolute zero, a freezing temperature. But the reason that they stay as ice is because they are mostly made of hydrogen, and hydrogen does not freeze. It is not possible to get solid hydrogen. So instead, it forms this kind of slush-like state. So places like Neptune and Uranus, they are mostly made of this kind of slushy ice. It's, you can get them in the shops, you pour them out and you do that. That is basically the entire planet. It would be a gas giant if it was closer to its star. Now, when we start looking at the exoplanets, they all start to look pretty similar. They are mostly big gas giants that are really close to their star. And the question might be, okay, that's interesting. We have two of those in our solar system, Saturn and Jupiter. Why is it that all of the other solar systems that we're looking into have loads of them? Or in fact, those are the ones that we're finding. We find very few Earth-like planets, very few things like Venus, Mercury. It's all the Jupiters, Saturns, and even the Neptunes and Uranuses that we're finding. Why do they all look so similar? Why are they all so big? Why are they all so close to their star? I've just said before that we reckon that our solar system is pretty normal. So why do the systems we're looking at not look like ours? And the simple again is that look like. See, all of the methods that we have work a lot better if it's a big planet and if it's close to its star. The transit method, the bigger the planet is, the larger the dip it's going to cause, the easier it is to spot. The closer it is to its planet, the more often it's going to transit in front of it. And the more often it transits in front of it, we're going to pick up those multiple signals. We also find, of course, that bigger planets are typically going to be gas giants, so those appear more often. Radial velocity method, direct imaging, microlensing, they all rely on that planet being large enough that it can affect its surrounding star. Mercury isn't going to make any dent on something as big as the star. Jupiter is thereabouts. So we might be able to, if it were a foreign solar system, detect Jupiter, but we probably wouldn't be able to detect Earth. That's why it's interesting when we find these things called super Earths. They are rocky planets that are 100 times larger than our own. So the question is not necessarily why are most of the exoplanets alike, but rather the question of what are the exoplanets that we can't see? What do they look like instead? Now, in a moment, I'm going to run through some of these planets. And I keep saying things like, oh, this has got hydrogen in it, or we know that this is a rocky planet. But if all we've got is a little light dip or a little bit of a change in the radial velocity, how can I make any of these kind of statements? Sure. Right? It makes a lot of sense that I could say, well, we know that because the star is this big and it wobbles this much or it loses this much transit, the planet must be this big. And we know because it goes past every so often that we know that this is its orbital period, and therefore we can say how far away it is from the star. But how can I even begin to suggest, well, this is a rocky planet or this is a gaseous planet that's mostly made out of hydrogen? How can I make any of these kind of statements if all we've got are these light dips? Well, the answer is quite simple and lies in spectroscopy. Now, spectroscopy is the science of using light to be able to tell us things. Normally, it's to tell us about chemical compositions. It's something we use all the time down on Earth, and it's one of our most powerful tools for looking into space. Now, you'll have to forgive the GCSE level PowerPoint animations here, but let's say we start with a particle of some chemical. And what we can do is we can fire a light beam at that particle. And what's going to happen is that light beam will deposit energy in the particle. It's like taking a small child and force feeding them loads of chocolate. This is going to cause it to wiggle around. That's basically what energy and heat is. It is energy within a particle is going to cause it to wiggle around. And as it wiggles around, it's going to lose some of that energy. And as it loses that energy, it will emit that as a light ray again. Light comes in, wiggles around a bit, light goes out. But what is important is that light that comes out is always the same. The reasons are actually based in quantum mechanics, so they really don't matter as far as this conversation is concerned. But what's important is it doesn't matter what light goes in, the light that comes out at the end is always the same. And we look at these in what we call spectrum. So this picture here is a picture of the hydrogen emission spectrum with some very particular lines in it. And this is if we were to fire a random batch of light at our hydrogen, the hydrogen will re-emit that light at these 5 particular wavelengths. And this basically is a fingerprint. Every single chemical, every single combination of those chemicals has their own different spectrum. If you get this spectrum, you can compare it to a library of all of the different chemicals, and you can say quite happily that there is hydrogen. And what's important about this is not only do we get these emission spectrums, but we can also get absorption spectrums. So if you were to take a beam of white light, which is light that is across the entire spectrum, and you fire that out into a detector, if you were to put some hydrogen between it and the detector, it is going to absorb those particular forms of light. It's happier to do a reverse of that emission spectrum. So if you put in some light, it will emit out those ones, but it's also preferentially going to absorb those same wavelengths of light. So either by causing what we call excitation, we can get a spectrum, or if we can get a nice white light, we can therefore get this absorption spectrum. Now, this is quite handy because stars give out white light. So what we can do is we can take a look at an exoplanet's atmosphere. It's done like this. If you have a star, that star is emitting white light, and as the planet passes in front of the star, what's going to happen is some of that light is going to pass through the atmosphere. Not all of it, of course, most of it's going to be blocked, but some of that light is going to be passing at just the right glancing angle that it passes through the atmosphere, out the other side, and then through into our telescopes. And then it is by comparing what does the spectrum look like when there's no transit occurring versus when there is a transit occurring. And we can take a look at things like this. So this is a stellar emission spectrum, an absorption spectrum. So what we can do here is by looking at these and looking where these black lines are, we can tell what chemicals are in that atmosphere. And by looking at the chemicals in that atmosphere, we can say, what is that planet made out of? Okay, so when I said we were talking about exoplanets, we've got 6.7 thousand confirmed exoplanets and 9.3 exoplanet candidates. With that many different exoplanets out there, there's got to be some really interesting ones, and there certainly are. So this is Methuselah, which is the grand name for PSR B162026b. This is a pretty big planet. It's 25 times the size of Earth, 2.5 times the mass of Jupiter. It is an ice giant. 12,500 light years away from the Earth and a 100-year orbital period. This is a big, cold, gaseous rock of a planet. Made out of that slushiness, it is an ice giant. Now, what makes this one interesting is we can actually date these planets. Almost all planets are made at the same time as the star that they are around. As I said, the stars that you get, the large gas giants, things like Jupiter, are often called failed stars because what was happening was all of the material was gathering ready to form a star, and effectively something else got there first. And sometimes you get multiple stars in these systems, but generally what you're going to find is that when one star lights up, it's going to cause a nice coronal ejection, which is going to blow away a lot of the extra material. So it's almost like a race. And most of the planetary formation is happening during that formation period. And what's really cool about Methuselah is because we can date the star, we can date the planet. And it is called Methuselah. I don't know how well you know your Bibles, but it is called Methuselah because this is the oldest planet we have been able to find. We can date this to 12.7 billion years old. That's not all that long after the start of the universe, or at least, it took a while for things to be even be able to form. So 12.7 billion years old is quite old for a planet. That's cool and interesting, but the planet itself is just a slightly boring ice giant. So instead, let's take a look at Gliese 436b. It's about the size of Neptune, 20 times the mass of Earth, and it is a gas giant. But what's important here is its orbital period. It's just 2.6 days. That means that it is just 2.5 million miles away from its star. That is really close. For some context, Mercury is 36 million miles away from ours. So this is a gas giant that is right next to its star. Now, we've done spectroscopy, and the really interesting thing about this is there's a lot of water on the surface of this planet. There's quite a lot of hydrogen and quite a lot of oxygen. And this is going to do something really, really weird. See, you can change how things form based on the pressure that they are under. You might have heard before, if you go to the top of Mount Everest, your kettle will boil at a lower temperature. And if you were to go to the bottom of the sea, your kettle would boil at a higher temperature. And this is because of a pressure difference. The higher the pressure is, the higher the pressure is, therefore the higher the temperature you need to reach in order to boil something. And the lower the pressure is, like it would be on the top of Mount Everest, the lower the temperature is. Now, with this planet being so close to its star, two different things are going to happen. Firstly, it's going to be really, really hot, right? We're talking thousands, tens of thousands, maybe even pushing to the hundreds of thousands of degrees on the surface of this planet. It is taking the full brunt of the heat of its star. But because it is so close and because it is really whipping around its star, there's going to be enormous pressures that are acting upon it. The gravitational forces that are squishing and causing the planet to orbit are going to be acting upon the surface of that. So what's going to happen, what scientists have calculated, is the fact that the entire surface of this planet, because it is at such a high pressure, is going to be made out of ice. But it is really, really close to its star, so it's also very, very high temperature. So the whole time, the constant top layer of that water, the water ice, is going to be on fire. The entire planet is a system covered in ice that is constantly melting, sublimating, and burning at the same time. There are other weird planets out there, of course. This is one of my favorite ones, Janssen 55 Canceri E. Now, this is only twice the size of Earth, but it's got a mass 8 times that of Earth. Now, that's really weird. The Earth has got a nice solid iron core, and for a long time, scientists basically thought, well, actually, that's probably about as heavy as things can get. There's a lot of complicated nuclear synthesis behind it, but iron is the single heaviest element that you're going to find broadly, widely, and in large quantities. It's what happens right at the very end of stars is they will forge quite a lot of iron. Anything beyond that, you need supernovas, which, whilst not rare events, are less common. So a nice iron-cored planet, pretty much we were expecting that you can't get much heavier than Earth. But this is only twice the size of Earth, but 8 times as heavy rather than twice as heavy. So what's going on? Now, to add to this, looking at it doesn't make a lot of sense. See, we find that there's a lot of carbon dioxide in the atmosphere, but not a lot of hydrogen. That's pretty bizarre. Well, again, our results here come from this orbital period. 17.5 hours. This is even closer to its star. It's going to be even hotter, and it's going to have enormous amounts of pressure. And this planet is covered in carbon. Now, carbon is not heavier than iron, not in its normal form. But if you take this amount of carbon and you put it under very high heats and very high pressures, what happens? It turns into a diamond. And that is what's happened to Jansen. A diamond core worth $27 nonillion, which sounds like a made-up number, but I assure you it's very real, and this is what that looks like written out. That is an absolutely silly number, and I wouldn't recommend going there to pick it up because on the surface of the planet there is enormous pressures which would crush you. It's very, very hot, which would burn you. And even if you're able to get past all of that, it has winds in excess of tens of thousands of miles an hour, and the entire atmosphere will be full of tiny little diamonds. So you will be standing in a roaring hurricane, far more powerful than anything ever seen on Earth, whilst being cut to ribbons by diamonds. So it's not worth even all that money. Okay, now there's lots of interesting things out there, but I want to take some time to look at some of the scientific possibilities. And I realize we've not got a huge amount of time, so I'm going to skip through these relatively quickly. Of these different scientific possibilities, the different things that could or do exist, but we maybe don't know quite as much about, because there's a lot more out there than just standard things that look like us. One of these is rogue planets. See, rogue planets are planets that not only don't orbit around our star, but also don't orbit around any star at all. A planet orbiting around a sun is a very delicate balance, right? You've got to make sure that the orbital mechanics are correct. And if you throw things off, if a big comet comes in, that could send the planet off into the universe. If you have multiple stars of a multi-body system, that could also send the planets off. In fact, we think that possibly most planets end up as rogue planets. There is an estimation that rogue planets may outnumber normal planets by something on the region of 10, 20 to 1, or even more. Some estimates, which seem absolutely crazy but may well be true, estimate it might even be something in the region of 10,000 to 1 for rogue planets. But we've only discovered 8 of them. And we reckon there's actually maybe another 11 more that we've found. So the question is, okay, well, if there's so many of them, if they're maybe outnumbering us as many as 10,000 to 1, even if that's a pretty high number, why have we discovered so few of them? The short answer basically is they're really hard to find. Right? It's about being able to see them, not that they don't exist. The way that we find all of these other planets is basically by looking at their star. And if the rogue planet has no star to look at, well, how do you find it? And the short answer is a lot of luck. There's some very clever things that people can do in order to be able to track them and that sort of thing. But basically all of the methods that we use in order to look at exoplanets, we can't really use for rogue planets. So that's why so few have been found. These are traveling messengers, and there is a suggestion that these could be the things that carry life around the solar system. If you have life that exists within a particular solar system and it manages to seed across multiple planets, if those are then flung out into the rest of the solar system where perhaps one day they're going to smash into something else, well, it's been suggested, and you've probably heard about this in terms of icy comets carrying life within its waters. Well, maybe it's the same thing for rogue planets, just on a much, much larger scale. I also want to talk about the last place you'll ever live. So the universe, as far best we know at the moment, is eventually going to run out of energy. The stars have only got so much fuel, and it's going to be a good few tens of billions of years, so it's not something any of us need to worry about. But eventually all of these stars are going to run out of energy, and as they run out of energy, the stars are going to go out. The last stars twinkling in the skies will be red dwarf planets. And red dwarf stars can have planets around them. It's exactly the same rules as for something like ours. But these dwarf stars are small. 10% of the size of the sun, 7.5% the mass of the sun. But that is an advantage for them. Because they're at this very, very small scale, the nuclear processes that go on within them are a little bit different, and they are effectively far more efficient engines. And whilst most of the stars will run out within a couple 100 billion years at the outside, these red dwarfs can burn for trillions of years. So that gives us a very, very long lifespan of planets that we could potentially live on. And again, we can have rocky planets, we can have gas planets, and you can have ice planets. Now, you're going to find more ice planets, and anything that we would consider habitable would have to be a lot closer to the star because it would be a lot smaller and giving off a lot less energy. We've not found any of these yet. Again, it's the same problem with rogue planets. Because the red dwarfs are much smaller, it's much harder to be able to see the planets that are near them. So it's not as easy as it is finding the big planets around the bigger stars. Now, let's get real sci-fi. Anti-worlds. In our universe, we have matter and we have antimatter, and never the two shall meet. When the antimatter and the matter touch each other, they annihilate in a big explosion of energy. But space is pretty big. So it is entirely possible, but merely theoretical, that there are planets out there that do exactly the same thing as our planets here, but they are made entirely of antimatter. Antimatter is the same as matter, but with a sign switch the other way, which means it can do all of the same things as matter, so long as there's no matter around and the two touch each other and annihilate. Because space is so big, now, the universe that we are aware of is all made of matter. But we suspect that at the beginning of the universe there was there was the same amount of matter as there was antimatter. So perhaps then there are pockets of the universe where it's matter over here and antimatter over here, and we're just not yet aware of them. This means that we could have entire planets, in fact, perhaps entire parallel Earths that are exactly the same, but they just are made of antimatter rather than matter. Now that's pretty sci-fi, but I also want to touch very briefly on sci-fi planets. How realistic are some of these planets? So if we look at sci-fi planets, the first thing I want to pick out on is this idea of single climate planets. So, this is a bit of a bingo card. Spot them if you know them. Solaris from the book Solaris, Londinium from Firefly, Dagobah, Capricia, Battlestar Galactica, Arrakis, Vulcan. These are all what I call single climate planets. Planets where they're like, oh, the whole planet is a forest planet. The whole planet is a sand planet. It's an entire planet that exists in just one capacity. These are not very realistic. If you think about all of the different climates that we can hit here on Earth, the idea that something like Londinium, which would be an entire planet with that sort of UK temperate climate, just doesn't make sense. So perhaps then something like Arrakis in June would make more sense, where the whole planet is just this one very hot desert. Well, again, that doesn't really shake out. And we can tell that from one of our nearest neighbors is Mars. So Mars is very small. It's about 0.15 times the size of Earth with about 0.1 the mass. It's made of rock and it's a bit further out. There's not a lot going on Mars. It's mostly this dead rocky planet. But what's important is up here at the top. This is a vast ocean. It is a frozen lake, but it is not a frozen lake of water. It is a polar ice cap, though, and it forms for exactly the same reason that we have polar ice caps here on Earth. It is colder at the top of the planet than it is at the equator. So even for somewhere like Mars, we see this different. It's a little bit more extreme, though, because it's made of carbon dioxide, and that carbon dioxide freezes at about minus 78.5 degrees. So it is very, very cold, but even on something like Mars, we have multiple climates between them. Jumping through here, hopefully lots of you can spot which this one is. This is, of course, Tatooine from Star Wars. And this is this kind of same rocky planet. But we also have this idea of the two suns, a binary star system. Is that something that is feasible? It comes up time and time again in sci-fi. There are multiple suns. What does it look like? Is this realistic? Could it happen? And the short answer is not only yes, but in fact, most planets probably have two stars. Now, this is a delicate balance because when we have two multiple bodies, they get very unstable and can fling things away. So effectively what will happen is the two stars will be orbiting each other, and then the planets will be far enough away that they can orbit effectively both of the stars at the same time. Again, it's orbiting this center of mass. And so long as that center of mass is between the two stars and the planet is far enough away around outside them, that's absolutely fine. In fact, this is how a lot of the rogue planets potentially get created. If they're too close and they start orbiting one star more than the other, they'll end up getting into these big eccentric orbits and then being flung out of their system. Another one, which is now slightly more culturally relevant, this is Pandora from James Cameron's Avatar. And if it's not immediately obvious from this picture here, this is based on Jupiter. So the planet of Pandora is actually a moon that is orbiting around another system. And Jupiter could be a place that we have life-giving planet-esque systems, right? Jupiter has 79 known moons, depends on how you count them, but Io and Europa are both very planet-like. And if they just weren't orbiting around Jupiter, they would be very obvious planets. They're very large, they're bigger than Mercury, Ganymede is certainly bigger than my brain's gone totally dead. Pluto. And basically what these are potential candidates for life having on them. This is largely in that they're covered in these sort of watery oceans, and these oceans may well have some kind of life inside of them. So something like James Cameron's Avatar, where they have this moon type planet that has all of the blue people and the big trees and all of that sort of stuff. That's entirely possible and entirely feasible. So perhaps this idea that a planet has to be orbiting the sun and can't orbit something else might actually clash with what we might think of a planet as being able to do. The fact that generally in our head we want to think of a planet as quite Earth-like, but perhaps some of the moons fit some of our conceptions of this better than the other planets. And I want to finish off with something a little bit wild, something really far out there. This might be something that some people are able to spot, but this is a rendering of Cybertron from Transformers. This is the Silicon Planet. It is a planet where the transforming robots are born and created. They came from a planet where their life force is based in silicon rather than carbon. Is this possible? Sure. Technically, right? We use carbon for our basis of life form, and it is possible to use silicon for that same purpose. Chemically, it does a lot of the same jobs. So what we can do is we could imagine that somewhere out there, perhaps an entirely separate species grew up with a silicon-based life form, and that will make them more like computers because of some of the different properties in silicon. The idea that they will be transforming robots that come to Earth for whatever shenanigans they've got up to in the latest movie that just came out, that is somewhat more far-fetched. But silicon-based life forms, well, maybe. And that maybe is a really big maybe. This picture here is possibly one you've come across before. This is the Hubble Ultra Deep Field. The way that we get this image is by going out into a field. If you go out into the field and you were to take a pin and you were to hold it at arm's length and you were to look at just the head of that pin, that is the amount of sky that is being looked at in this picture. The way that it worked, the Hubble telescope looked at that tiny patch of sky for 6 months. They weren't really expecting to find anything. It was such a tiny, tiny, tiny patch of sky. But they thought we'll leave it for a really, really long exposure, capture as much of that image as we can, and we'll see what we find. And this is what they found. In this picture, there are just 6 stars. And you can pick out the stars because they have that sort of cross shape across them, which comes from the construction of the telescope. Every other speck of light in that picture is an entire galaxy. Each of those galaxies contains billions, if not trillions, of stars. And by some of our best calculations, each of those stars is going to have its own solar system. And each of those solar systems is going to have maybe a dozen planets. Our solar system is probably pretty normal. So let's say 7 or 8, 9. Maybe it's got a little bit less. Maybe it's got a little bit more. But on average, let's call it roughly equal to our own. So if each of these planets, if each of these specks of light is one galaxy in a truly, truly tiny portion of the sky, if each of these galaxies contains billions and billions of stars, if each of those stars on average has at least a handful of planets, well, that's a lot of different planets out there. The idea that something like the Transformers could exist, that something like Pandora or Tatooine could exist, it might be a tiny, tiny chance, the smallest opportunity on the roll of the biggest die you could think of. But with that many galaxies, that many planets, that's a lot of rolls of the dice out there. So whatever you can think of, it's probably there. It's really just a question of if we'll ever be able to truly take a look at all these worlds. Thank you very much.
Well, fantastic, James. Thank you very much. That was wonderful. Just let me come back in with my audio and video. Everybody else, you can come back in with your audio now. Well, yeah, wonderful. Can you just stop sharing for a minute, James? Thank you.
Yeah,
And then we'll, if we need to go back to your presentation, we will. What we do by tradition is, first of all, give you a very large and resounding virtual round of applause. It's a bit difficult with the Zoom, but can I ask you all to give your reactions or a round of applause, please, for a wonderful talk? Thank you, James.
Thank you.
A lot of virtual hand clapping as well, there, you can see. There are various ways. It's never quite the same, is it, as being in a room with the people. You know, I know what it's like, done it myself, but you know, you can't gauge the reaction, but I think everybody will join with me in agreeing that that was wonderful, fabulous photograph. That's a good thing about exoplanets, isn't it? They do make for great photos, especially if it's an artist's impression or something.
Yeah, you can really go mad.
You can have a lot of fun with the colors and the shapes and things. Absolutely wonderful. Thank you. A couple of questions from me, first of all, and I'll hand over as usual. Just when you opened with your remarks about the shape of the Earth, you referred to it as an oblate spheroid, which of course is very technically correct. It reminds me of a friend of mine years ago who had an Oxford degree in geography, and he was asked by somebody in the office what shape the Earth was, and he said, "Well, it's geoid." And to which the reply came, "Geoid? What does that mean?" He said, "Well, Earth-shaped." which I thought was rather funny. But anyway, couple of things. Just at the beginning, talking about our own solar system planets, I understand all the stuff surrounding Pluto in terms of its, you know, its relegation from our official, you know, Premier League of planets, if you like, to becoming a dwarf planet. But it did occur to me that you didn't actually. I don't know whether you mentioned Kuiper Belt, but you said it belonged to these other rocky worlds, which was similar, and that kind of disqualified it. But is it not true that Pluto's very inclined orbit, the ecliptic, takes it out of the Kuiper Belt and separates it in a kind of physical way? Or am I wrong there? In which case, why were they so harsh on it? I know this isn't an exoplanet question, but
yeah, no, that's fine. Okay, the short answer is, and there's some very technical answers that I'm sure people could give you, but I certainly couldn't. Yes, you know, not to I was 9 when this decision was made, so I had no part in it.
No, I'm not blaming you. No.
But basically, the long answer is, if we allowed Pluto to be a planet, you'd suddenly have to let a lot of other things be a planet, and the decision was made that planet needs to be quite a special category.
Yeah.
Now, what reasons that was made for, they're probably more, sort of emotional necessarily than having a specific scientific definition. But that's the long and short of it. Is basically that it was made. The decision was made that if we include Pluto, there's no way to not include a load of other things that we've found within the Kuiper Belt and within the Oort cloud, most especially. It's whenever people talk about, oh, the mysterious planet X, the next planet that we found. That's a load of nonsense, because actually there's dozens and dozens and dozens of them out there. So it was just a case of, we wanted to keep the planet special, and that ultimately meant that Pluto had to go out.
Fair enough. Yeah. Okay. Just another thing. You mentioned the most popular or the most successful detection methods, and I think you had a figure of about 3% for other. I assume is that what I would call the wobble method, where the host star, especially if there's a massive planet but hasn't been detected by any other means, produces a very slight oscillation in the star, and that means there is something affecting it, the barycenter within the star perhaps, but is that within that 3% of other methods? Or
so no, that's the radial velocity method. So that wobble is the radial velocity, which is at 18.5%.
Okay. Oh, I thought the radial velocity was just by using the wavelength of light on the redshift and blue shift.
So yeah, so that's the redshift and the blue shift is how we measure the wobble.
Okay. Oh, I see. I'm with you. All right. And finally, you mentioned Janssen 55 Cancri E. I made a note. You're right. They're not great at naming them, are they? But they've got to give them some kind of a name. You mentioned the mass of this particular one, how massive it was. How is the mass measured then? I wasn't quite sure how. I may have missed that. How did they know the composition? But even so, is it they can't know the entire composition from, throughout the core? How do they assess the actual mass?
So the mass comes as a product of its velocity, so its orbital period, and also its distance from the star. So if it's heavier, it's going to move quicker than if it was lighter. Is the short version. So you do lots of maths, and it's not necessarily simple, because you've got lots of different factors you've got to bring out. You don't necessarily know how far away it is from the star, how big it is. You've got to sort of work them all out at the same time, which obviously makes things quite complicated. But yeah, basically it comes down to doing some maths on the data that we do have. You can work all of these things out individually.
So it's orbital mechanics, and mass is part of that orbital calculation.
Yes.
You can extrapolate from that. I see. Great. Wonderful. Okay. Right. I'm going to hand over to the floor. Would anybody like to ask James a question?
I'll start with, I've seen ones coming on the chat.
Yeah, well, if there's chat ones as well,
so I don't have a microphone. Silly question. No such thing. Dark matter is thought to exist as baryonic matter in the visible universe. Does this not account for gravity that affects orbits? As we continue to discover more planets that we could not previously see, could some of this account for the missing matter? That is a fantastic question. The short answer is no. That's already taken into account when we do when we're talking about this missing dark matter, which we need for the gravitational effects. When we do the calculations, there's two things that suggest that this isn't the case. First one is we've already taken that into account. Right? What we do is we say, right, each solar system we're going to add some additional percentage of mass for how many planets there are, and it's also worth noting that that amount that we're adding is basically a rounding error. Now, could there be more mass in something like the rogue planets, which obviously we can't account for so simply? Well, maybe, but it's still this sort of rounding error type number. And importantly, we would expect to see in that case that the planets will be distributed roughly the same as the stars. So all of these planets, you're mostly going to find them in the middle of the galaxies, and you'll find less towards the outside of the galaxies, which you do with stars. But actually, the way we find dark matter is the opposite. More of the dark matter is around the outside of the galaxies and less on the inside, which is the inverse to the stars, and therefore the inverse to what we would expect the planets to be. So maybe is the short answer, right? Because the whole point is we don't know, but it's very, very unlikely because it does the opposite of what we'd expect it to do. So unless some sort of groundbreaking new thing came in, we wouldn't expect it to be just because of that inverse relationship that we see. But it's a really good question, though.
Somebody else?
I got a question, James.
Go ahead.
Are there any new techniques or new thoughts as to trying to detect, more of the smaller rocky items? obviously better observatories, but are there new radical approaches? I don't know, interferometry, or I know I've heard about trying to use the gravitational effects of our sun to act as a focal zone, but you've got to go out like 200 astronomical units to be able to use it. So not currently available, but in 100 years maybe. I wondered if there was any thoughts about new principles, new techniques.
Well, the short answer is yes, loads. There's people working on this stuff all the time. Exoplanet is a really big field at the moment. It's one of the growing fields, and in fact, these days it's one of the few areas of practical astronomy that's left. You know, a lot of astronomy these days is either experimental in labs, testing stuff as though it was in the stars, or you know, it's sort of theoretical, making computer models of all of this stuff. So yeah, basically, lots of people are working on it. They're coming up with all sorts of really interesting ways and lots of interesting testing ideas. But a lot of them are quite expensive. So, you know, there's prototypes and stuff going on, but nothing has yet come to surpass it. It all comes down to money one way or the other in the end. So there are people doing things. There are new things being tested. When the Square Kilometre comes online, lots of the time on that's going to be used. James Webb Space Telescope, some of the time in that has been dedicated to exoplanet searching. You know, there's a lot of stuff that's just coming down the pipeline, and there are lots of people thinking up weird and wonderful ideas. But whether they'll come along, you know, that's a question of both time and also where the funding lands.
Right, thanks.
I follow up on Chris's question about the orbital mechanics. Can we infer anything from looking at your orbital mechanics of the planets that we do identify? Any wobbles in those planet orbits themselves, or is it just that the data isn't that accurate enough to take that extra step?
So when so when we're looking at the wobbles, generally we can only detect the star. We're not sensitive enough to detect the planet itself, because planets are effectively dark objects, and that's why we are relying on the star that they're around, because those are bright objects and those are actually emitting to us. Now, we can do some interesting things. If you've got multiple planets, you can differentiate multiple different planets within a single wobble, because it'll be some sort of aperiodic or at least an aharmonic wobble. So you can do some cool stuff with that, but the actual planets themselves, very, very rarely do we get to do any direct observation of those planets. I've just seen a one in here from Francis. If the stars are closer together in the galactic center, then planet orbits would be highly disturbed and lead to them being ejected from their systems. Yes, absolutely. The closer stars are, the more likely you are to have that. To some extent, though, if you have stars that are close enough to each other that they are going to cause that kind of disturbance, they probably will have formed like that. Or the planets are going to get burnt up in the collision anyway, and they're just going to like fly into the suns to do that. Of course, lots will get ejected, but over the span of a galaxy, it's not going to travel very far. So even if you have a bunch of stars that came together and they collide and they throw all of their planets out, all those planets will still be in the galactic center, because the galactic center is so huge. Even if they're traveling for millions and millions of years, they are still in the same region of space, simply because space is enormous. I mean, they will be traveling at some fraction of the speed of light, and our entire solar system, you know, generally we say that the influence of our sun spreads for about 1 light year. So for about 1 light year in all directions is stuff that is orbiting the sun. Obviously, it gets much weaker as it goes out. But so, you know, if your planet is traveling at even 100th, 1,000th of the speed of light, which is still very, very quickly, it's going to take trillions and billions of years to get any actual distance away from those stars. Okay, I think we've got time for maybe one more.
Anybody?
Micro lensing I was going to ask about. Is there a sort of a distance beyond which micro lensing does become effective? or is it that if you've got a really heavy object closer, you get that effect closer to us?
Ooh, do you know, I think the short answer is I don't really know enough about gravitational lensing to be able to answer that question. I mean, so certainly the heavier the object, the more likely it is to cause lensing. And the closer that object is to you, the more likely you are going to see that lensing. Because if you imagine it as a physical lens that existed, right, the lenses right in front of your eyes affect a lot more of your field of view than if you had, the same lens being held up on a stick outside of your arm. So the closer the object is, the more gravitational lensing we will observe. Not more that it will actually cause. It'll still cause the same amount. It's just we will observe more. And the heavier the object, i.e. the larger that lens is, the more likely we are to see it again. But I don't know enough about gravitational lensing to be able to make any real statements apart from that sort of basic physics. Okay. Right, well, in which case, thank you very much, everyone.
Yeah, I think we're done if nobody's got any more questions. Well, James, thanks once again. That was absolutely truly wonderful. And I've marked your card now, so I will be. I don't let people go if someone gives us a great talk. I noticed you have a nice a repertoire or catalogue or whatever you want to call it. So I'm sure you'd have no objections if in a future season I got in touch with you again, invite you back again. It was wonderful. We're only a small society, as I say, but we're very enthusiastic and we really appreciate the time you've put in. Really fantastic. Thank you. Can I ask everybody once again?
We had to switch off.
To give us, well, just another round of applause, if you would, please. Okay. Thank you very much indeed. Really appreciate it. Okay, that wraps it up. We've got Owen Brazell next month, and I'm sure we'll see James again. Thank you, James, and good night, everybody. All right.
Yes.
Bye-bye.
Thank you, Chris. Good night.
Bye-bye.
Good night.